Welcome to the Nocturnal Astronomer, where we explore the mysteries of the universe in the most gentle and accessible way possible. I'm your host, Atlas Reid, and tonight we're going to tackle one of physics' most mind-bending concepts, string theory. Now, before you click away thinking this is going to be impossibly complex, let me assure you that we're going to break this down using nothing more complicated than rubber bands, guitar strings, and everyday analogies that anyone can understand. Think of tonight's journey as watching the universe reveal its deepest secret, told in the simplest language possible. We'll discover how everything you see around you, from the tiniest particles to the largest galaxies, might actually be made of something far more elegant than you ever imagined. If you find yourself drifting off to the soothing mysteries of the cosmos tonight, please give this video a thumbs up and subscribe for more gentle explorations of space and physics. And here's a fun challenge. In the comments below, tell me what everyday object you think would make the best analogy for explaining the universe. I read every single comment and love hearing your creative ideas. Alright, let's dive in. For thousands of years, humans have wondered what everything is made of. If you take a rock and break it in half, then break those pieces in half, and keep going, what do you eventually get? The ancient Greeks thought you'd eventually reach something that couldn't be broken anymore. They called these indivisible pieces atoms, which means cannot be cut. For a long time, scientists believed atoms were the smallest building blocks of everything. Then they discovered that atoms themselves are made of even smaller pieces, protons, neutrons, and electrons. It was like opening a nesting doll and finding another doll inside. But the story didn't end there. Scientists kept digging deeper and found that protons and neutrons are made of even tinier particles called quarks. At this point, you might be wondering, does this ever end? Are there smaller and smaller pieces forever, like an infinite set of nesting dolls? This is where string theory enters the picture. Instead of finding smaller and smaller particles, string theory suggests something completely different. Imagine that at the very bottom of this cosmic nesting doll, instead of finding the tiniest possible, you find something that looks like an incredibly small piece of string. These strings are unimaginably tiny. To give you a sense of scale, if an atom were the size of our entire solar system, one of these strings would be about the size of a tree on Earth. They're so small that we can't see them directly, even with our most powerful microscopes. But according to string theory, these invisible strings are what make up absolutely everything in the universe. The beautiful part is that these strings aren't just sitting there motionless. They're constantly vibrating, like the strings on a guitar. And just as different guitar strings produce different musical notes when they vibrate, these cosmic strings create different particles depending on how they vibrate. A string vibrating in one pattern might create what we call an electron. The same string vibrating in a different pattern might create a photon, which is a particle of light. This means that every particle in the universe, from the electrons in your body to the photons streaming from distant stars, are all the same thing at their core. They're all tiny strings, just dancing to different rhythms. It's as if the entire universe is one enormous, invisible orchestra, with countless microscopic strings playing the symphony of reality. To truly understand how string theory works, let's spend some time with a familiar instrument, the guitar. When you pluck a guitar string, it vibrates back and forth, creating sound waves that travel through the air to your ears. But here's something interesting. The same string can produce many different notes depending on how you play it. Press your finger down on different parts of the string, and you change its length. A shorter section vibrates faster and produces a higher pitch. A longer section vibrates slower and produces a lower pitch. You can also change the sound by plucking the string harder or softer, or by using different techniques. One string, many possible sounds. Now imagine shrinking the guitar string down to the smallest possible size, smaller than atoms, smaller than anything we can directly observe. These cosmic strings work in a remarkably similar way. Just as a guitar string can vibrate in different patterns to create different musical notes, these fundamental strings can vibrate in different patterns to create different particles. When a string vibrates in one particular pattern, it might manifest as an electron, the particle that orbits the nucleus of atoms. Change the vibration pattern slightly, and the same string might become a quark, one of the building blocks of protons and neutrons. Adjust the pattern again, and it could become a photon, a particle of light. This is why physicists sometimes call string theory the music of the spheres in a very literal sense. The universe, according to this theory, is essentially a cosmic symphony. Every particle that exists is like a note being played by an invisible string. The electrons flowing through the neurons in your brain as you listen to these words, the photons from your screen reaching your eyes, the quarks that make up every atom in your body, they're all different songs being played by the same type of cosmic instrument. But unlike a guitar, which can only vibrate in a limited number of ways, these fundamental strings can vibrate in many more dimensions than the three we're familiar with. This brings us to one of the most mind-bending aspects of string theory, the idea that our universe might have more dimensions than we can perceive. Think about how a guitar string, which is essentially one-dimensional, creates vibrations that we experience as sound in our three-dimensional world. Similarly, these cosmic strings might be vibrating in dimensions beyond our normal experience, creating the particles and forces we observe in our everyday three-dimensional reality. One of the most fascinating predictions of string theory is that our universe has more dimensions than the three we experience every day. We're familiar with length, width, and height, plus time as a fourth dimension. But string theory suggests there might be 6 or 7 additional dimensions curled up so tightly that we can't detect them directly. To understand this concept, imagine you're looking at a garden hose from very far away. From that distance, the hose appears to be just a line, a one-dimensional object. But as you get closer, you realize the hose actually has width and depth. It's three-dimensional, but those extra dimensions were hidden from view when you were far away. String theory proposes something similar might be happening all around us. What we perceive as the three-dimensional space we move through might actually be filled with additional dimensions that are curled up so small we can't detect them. These hidden dimensions aren't somewhere else, they're right here, in every point of space around you. Imagine tiny, invisible loops at every point in space, smaller than atoms, smaller than anything we can measure. These loops represent the extra dimensions that string theory predicts. The strings we talked about earlier don't just vibrate back and forth like guitar strings. They can also move through these tiny, curled-up dimensions. The way a string moves through these hidden dimensions determines what kind of particle it appears to be in our familiar three-dimensional world. It's like how a coin spinning in the air can look circular from one angle and linear from another, except far more complex. The same string, depending on how it's oriented and moving through these hidden dimensions, can appear as completely different particles to us. This might sound like pure fantasy, but it helps explain some puzzling observations about our universe. For instance, gravity is much weaker than the other fundamental forces. If you can lift a paperclip with a small magnet, you're demonstrating that the electromagnetic force in that tiny magnet is stronger than the gravitational pull of the entire Earth trying to hold the paperclip down. String theory suggests that gravity might be leaking into these extra dimensions, which would explain why it seems so weak in our three-dimensional world. The other forces might be confined to our familiar dimensions, while gravity spreads out into the hidden ones, making it appear diluted from our perspective. These extra dimensions aren't just mathematical abstractions. They could be real aspects of physical reality that we simply can't access directly, like trying to see around a corner without moving. One of the most elegant promises of string theory is its potential to unite all the fundamental forces of nature under one simple, beautiful framework. To understand why this is so significant, we need to talk about what physicists call the four fundamental forces. First, there's gravity, the force that keeps your feet on the ground and holds planets in orbit around stars. Second is electromagnetism, which governs everything from the light streaming from your lamp to the magnetic field that protects Earth from cosmic radiation. Third is the strong nuclear force, which holds the centers of atoms together. Fourth is the weak nuclear force, which is involved in certain types of radioactive decay. These forces seem completely different from each other. Gravity works over vast distances but is incredibly weak. Electromagnetism can be strong or weak and works over long distances. The nuclear forces are extremely powerful but only work over tiny distances inside atoms. For decades, physicists have been trying to find a way to show that these apparently different forces are actually aspects of the same underlying phenomenon. They've had some success. Scientists have already shown that electromagnetism and the weak nuclear force are really two aspects of the same thing, called the electroweak force. They've also made progress connecting this with the strong nuclear force. But gravity has remained stubbornly separate, refusing to fit into the same mathematical framework as the other three. This is where string theory offers something remarkable. Instead of treating particles and forces as fundamentally different things, string theory suggests they're all just different vibration patterns of the same underlying strings. A string vibrating in one pattern might create what we experience as an electron. The same type of string vibrating in a different pattern might create a graviton, the hypothetical particle that carries gravitational force. Think of it like this. Imagine you have a master musician who can play any instrument. When they play a violin, you hear one type of music. When they play a piano, you hear something completely different. But it's the same musician creating both sounds. String theory suggests that all particles and forces are like different instruments being played by the same cosmic musician, these tiny vibrating strings. This unification would mean that at the deepest level, everything in the universe is connected. The force holding atoms together in your body, the light from distant galaxies, and the gravity that shapes the cosmos would all be expressions of the same fundamental phenomenon. It's a profoundly beautiful idea that beneath all the apparent complexity and diversity of the universe lies an elegant, simple unity. One of the most intriguing aspects of string theory is that it doesn't predict just one possible universe. Instead, it suggests there might be an enormous number of different ways the universe could be configured, each corresponding to different ways the extra dimensions could be shaped and the strings could vibrate. Imagine you're in a vast landscape filled with valleys, hills, and peaks. Each valley represents a different possible universe with its own laws of physics, its own types of particles, and its own fundamental constants. Our universe would be just one valley in this enormous landscape of possibilities. In some of these other possible universes, the force of gravity might be much stronger or much weaker than in ours. In others, electrons might have different properties, or there might be entirely different types of particles that don't exist in our reality. Some universes might be so different that atoms couldn't form, while others might have physical laws that allow for types of matter and energy we can't even imagine. This raises a fascinating question. Why do we find ourselves in a universe with exactly the right properties to allow stars to form, planets to exist, and beings to emerge? The answer might be surprisingly simple. If there are indeed countless possible universes in this vast landscape, then some of them would inevitably have the right conditions for complexity and development. We shouldn't be surprised to find ourselves in one of these friendly universes, because we couldn't exist in any of the others to ask the question. It's like wondering why you always find your keys in the last place you look. Of course they're in the last place you look, because you stop looking once you find them. This idea connects to something called the anthropic principle, which suggests that the universe appears fine-tuned for existence not because it was designed that way, but because we could only exist in a universe that has the right properties. All the universes with the wrong properties exist too, but there's nobody there to observe them. The landscape of string theory possibilities is unimaginably vast. Some estimates suggest there could be 10 to the 500th power different possible universes. To put that number in perspective, the total number of atoms in the observable universe is estimated to be around 10 to the 80th power. So there could be far more possible universes than there are atoms in our entire cosmos. This abundance of possibilities doesn't make our universe any less special or meaningful. If anything, it makes the particular combination of physical laws that allows for stars, planets, and conscious beings even more remarkable. You might be wondering how scientists can study something as abstract and tiny as vibrating strings that exist in dimensions we can't even perceive. This is one of the biggest challenges facing string theory. Unlike many scientific theories, string theory is extremely difficult to test directly with experiments. The strings are so small that even our most powerful particle accelerators can't probe the energy scales where string effects would become apparent. To directly observe these strings, we would need a particle accelerator roughly the size of a galaxy. Obviously, that's not something we can build with current technology. However, scientists are finding clever indirect ways to look for evidence of string theory. They search for subtle patterns in cosmic background radiation, the faint afterglow of the Big Bang that fills all of space. They look for particular types of particles that string theory predicts should exist. They study black holes and try to understand how information behaves when it falls into them, because string theory makes specific predictions about this process. Some researchers are also exploring the mathematical structure of string theory itself, finding that it connects to many different areas of mathematics in unexpected ways. Sometimes, insights from string theory have led to breakthroughs in pure mathematics, even though the physical reality of the theory remains unproven. There are also astronomical observations that might provide clues. If our universe really does have extra dimensions, they might leave subtle signatures in the way gravity behaves over very large distances. Scientists are carefully measuring how galaxies move and how space itself expands, looking for tiny deviations from what we would expect in a purely three-dimensional universe. The search for dark matter and dark energy, two mysterious components that seem to make up most of our universe, might also provide insights. Some versions of string theory predict the existence of new types of particles that could account for dark matter. Even if we can't directly observe the strings themselves, we might be able to detect their effects on the larger structures of the universe. It's like trying to understand the wind by watching how it moves the leaves on trees. We can't see the wind directly, but we can observe its effects. The mathematical beauty and internal consistency of string theory continues to attract researchers, even without direct experimental proof. Sometimes in science, a theory's elegance and ability to connect seemingly unrelated phenomena can be compelling evidence for its truth. As we reach the end of our journey through string theory, it's worth taking a moment to appreciate the profound picture of reality this theory paints. If string theory is correct, then everything you see around you, everything you are, and everything that exists throughout the cosmos is fundamentally made of the same thing: tiny strings vibrating in harmony. The coffee cup on your table, the light from distant stars, the thoughts flowing through your mind as you listen to these words, they're all different melodies played by the same cosmic orchestra. Every electron, every photon, every quark is a note in this universal symphony. The forces that hold atoms together, that power the sun, that keep planets in their orbits, they're all different instruments playing their parts in the same grand composition. This perspective offers a deeply unified view of existence. Rather than seeing the universe as a collection of separate, disconnected things, string theory suggests that everything is intimately connected at the most fundamental level. The carbon atoms in your body were forged in the hearts of ancient stars, and according to string theory, those atoms and the stellar furnaces that created them are all expressions of the same underlying string-like reality. The extra dimensions that string theory predicts add another layer of mystery and wonder. As you move through your daily life, navigating the familiar 3 dimensions of space, you might be constantly passing through additional dimensions that are curled up so tightly you can't perceive them. These hidden aspects of reality could be right here, in every point of space around you, invisible but nonetheless real. Perhaps most remarkably, string theory suggests that our universe might be just one movement in an infinite cosmic symphony. In the vast landscape of possible realities, there could be countless other universes with their own unique melodies, their own ways of organizing matter and energy, their own expressions of the fundamental string-like nature of existence. Whether string theory ultimately proves to be correct or not, it represents something beautiful about human curiosity and our desire to understand the deepest nature of reality. It shows our willingness to imagine possibilities far beyond our direct experience, to follow mathematical beauty and logical consistency into realms that challenge our everyday intuitions about how the world works. And on that note, as we drift towards sleep surrounded by the invisible cosmic symphony that string theory describes, remember that you are not disconnected from the universe around you. You are part of it, made of the same fundamental strings that compose everything else, vibrating your own unique melody in the grand composition of existence. Thank you for joining me on this gentle exploration of one of physics' most ambitious theories. Until next time, sweet dreams, and may your rest be filled with the quiet music of the cosmos.